All right. Hello, everybody. Welcome back. Physics of Music, lecture number 2 going on here. Still in week 1, but said things will go pretty quickly this summer. So let's just get on started and go from there. All right. So let me open some stuff up here. Let's start off right here. All right. So what do we got going on today? Well, first off, if you weren't here or you didn't um, view the lecture one, go ahead, do that. That's important. Submit the outlines for section 1, section 2. Take the quizzes, section 1, section 2. Do the reading assignments in section 1 and section 2. And note, again, everything's going to be based upon previous lectures. It's building block sort of course where you learn something and expand on it, and expand on it, and expand on it. And that's the way things work. So it's really important to be sequential and again keep up with things. Other than that, we've got the book, Get 'em, Audacity. We're going to start using that today. So if you have not yet downloaded Audacity, go ahead and do that. The link for it is in instructions 1 on our page, and also Raven Pro 1.6. Just download it onto your system. Don't worry about anything utilizing it yet. Just get it downloaded, make sure it downloads, and then we will use that in a couple weeks. But at any rate, what we want to do is come back over to our Canvas page and just note a couple things again. Syllabus is here. This is where the links are for the recordings. You can see section 1 there is there. This will come back to the opening raving settings and preferences, but lecture number 1 recording is there. What else can we say here? Section 1 and section 2. Don't worry about all sounds there. Course resources, section 1. And here we are on section 2. We'll go ahead and look at section 2 instructions. Read chapter 2 in the textbook. And then if you haven't done so, get Audacity. And hey, basically roll through things. So today we will introduce an experiment for this section, and it'll be based upon what we're doing today in class. So that's pretty much where we are. Haven't done anything really, but we start. So let me jump back over here. And let us begin. So the topics for today, we're just going to get down the basics of sounds. How do we parameterize sound? How do we discuss it? We'll talk about some wave parameters, what constitutes a tone, and pure tones versus complex tones. And this is just where we begin. All right, so let's just start with the basics of sound. In order to produce a sound, well, we need to think about some sort of energy being input into a system. Sound ultimately is all correlated with vibrations. You need some source of energy that makes something vibrate, whether you're knocking on a door using your own energy, knock, 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 making the door vibrate, or you are dropping something on the ground and makes some sound because it hits the ground and vibrates. There's some sort of energy that is producing the vibration itself. So that's the first thing we need. We need some sort of source of energy. And then in order to transmit the sound, we need some sort of material through which that vibration can travel. So for us, typically that material is going to be air. Sound travels through air, and it travels through air as a vibration. The individual air molecules surrounding the source itself will vibrate in the same way that the source vibrates, and that vibration will be carried through the air itself in sort of a domino chain reaction effect where the air molecules right next to the source will vibrate, and those air molecules vibrating will make the ones next to them vibrate, and next to them vibrate, and next to them vibrate. You get this chain reaction that ultimately makes this sound travel through air and eventually it reaches our ear or some sort of recording device or something to that effect, something to perceive the sound. So generally, we're going to think about us being the receiver or eardrum. And eventually, as all these little air molecules vibrate, we have that the air molecules right next to our eardrum will eventually vibrate as well. They'll vibrate our eardrum vibrates, then there's little nerve cells within our eardrum that are sensitive to specific frequencies that we perceive as the sound. And that's basically that. So those are the three things that we need: source of energy, a material through which the sound can travel, and some sort of receiver to perceive the sound itself. Now, sound does travel through other materials. We can have sound travels through water, travels through metal, travels through wood, travels through really can travel through anything. Anything, I shouldn't say anything because there's some things that reflect sound, damp sound out. But for the most part, what we need is some material, some sort of material. For that, it's going to be air. Sound's going to be traveling through air. But the main thing here is that do need a particular material. Sound does not travel through a vacuum. And by a vacuum, I mean the absence of material itself. So out in space where there's no material, you can't produce a sound. Well, you can produce a vibration, but that vibrational state isn't carried through empty space because there's nothing to house the vibration itself. So if you took a tuning fork, say, out in space and you struck it, the tuning fork would vibrate, but you're not going to hear anything because there's no material to channel that vibration from the source, say, to your ear. So that's why it's important for us to be in air to perceive sound, and that's what we've got going on. And we'll look at some animations regarding vibrations of air molecules here in a few, but I'll just get to how we discuss sound waves in a sense. So the way that we model sound is through a wave characteristic that as things vibrate, that vibration can be traced back to some sort of wave. Now, we don't necessarily mean like a water wave or something like this. The wave can just be a tracking of the placement of the individual portion of the source itself. So you think again about a tuning fork and one of the bars vibrating back and forth. If we looked at the position of the bar with respect to time, we note that it has some variation. It's going back and forth, back and forth, back and forth. And we could plot that out. And what that would do is it would give us something that is a wave-like picture, like this. So this is known as a sine wave. It's a mathematically produced wave. We're not going to worry really about the mathematical aspect of it, other than sine waves are how we are going to really fundamentally characterize sound waves themselves, whether it's a traveling sound wave or whether we're just looking at the vibration of the source. So sine wave is a really nice, continuously varying wave that just repeats itself over and over. So if we start like right here, we've got that it goes up, goes back down, goes in the other direction, goes back up, and then it repeats, right? It does it again, and then it does it again. So right here, what we want to be able to extract out of this for right now is just the notion of a cycle. A cycle is one complete repetition of, well, when we're talking about a wave, one complete repetition of the wave, one full pattern that then repeats itself. So if we look at this sine wave right here, we should be able to count how many individual cycles there are, given that we can count out the repetitions. We've got one repetition, and then does it again, there's two, and then there's three. So this is three full cycles of this wave right here that is shown. But I do want to also note that we can just define a cycle arbitrarily in a sense. As long as we encompass one full repetition of a wave, we can identify that as being a cycle. Because if it's doing the same thing over and over, it doesn't really matter where you start measuring. So I could also go from this peak right here and say from right here to right here, this next peak over is also one full cycle, because I go from here all the way at the top, go all the way down, then all the way back up, and I'm back to where I started. Then I would go all the way down, all the way back up, back to where I started. So I could identify this as one full cycle as well. So again, that's the aspect of just being able to see the repetition itself. So that's the main point with the cycle. So the screen is black. Is it still black? You guys see the sine wave here? Someone saying the screen's black? So like I said, I'm not sure why the screen's black for you. That sounds like it's something on your end if someone else is seeing this. Maybe try to exit and enter again. I'm not sure. All right. Continuing on. Continuing on. Oops. So again, the sine wave is going to be how we model sound waves themselves. And that's a nice beginning spot that we have. So again, being able to see a full cycle of a wave, given some sort of picture of a wave, is going to be really fundamentally important, because that's going to be one of the key characteristics of sound waves. So that brings us to the principal wave parameters, which are how we're going to discuss waves in general. The amplitude, period, frequency, wavelength, and wave speed. Those are the five main things that we want to be able to discuss when we're talking about sound waves, or just really waves in general. But again, we're sticking with sound waves here. So the amplitude of a wave. The amplitude of the wave is, well, really it's the maximum variation in a cyclic quantity, and something that is fluctuating in a repetitive manner. So the amount of variation in it, what does that mean? Well, it depends really what you're looking at. Are you looking at the maximum displacement or maximum change in position that's taking place? Are you looking at the maximum the maximum intensities variation? There's different things that we could be looking at in terms of amplitude. So if I go back to this wave right here and I say, well, what is this? What am I really characterizing here? I say, oh, well, it's a sound wave, but what is it really a graph of? This one and this negative one would have some sort of meaning, right? So we could say that, well, this is really the maximum displacement, this one right here in the negative one, the maximum displacement from the equilibrium position of the tuning fork itself, from one of its ends as it vibrates back and forth. It goes from its normal state, it goes to, say, 1 millimeter to the right, and then it goes back to its normal state, and then it goes 1 millimeter to the left, then back to its normal state, then 1 millimeter to the right, then 1 millimeter to the left, and it vibrates back and forth. So right now, these are arbitrary, but that's something that it could be. This could be a plot of the position of whatever's vibrating back and forth. Or it could be a plot of the intensity or pressure. There's lots of different things that we could be looking at in terms of a maximum variation. But the main thing with this is, hey, the amplitude is really just about what is the maximum variation in whatever wave we're looking at. That's it, amplitude. Then we've got period. Period is how long it takes to produce one full cycle, or the time extent of one full cycle. How much time is contained within one full cycle of, say, a vibration. So again, if we come back to this and say that this is a plot of the position of the tuning fork rod with respect to time here, that it's varying with time. It starts out at 0, and then as time goes on, it goes to 1 millimeter to the right, and then goes back to 0, then 1 millimeter to the left, then back to 0, 1 millimeter to the right, 1 millimeter to the left. And this is happening over some amount of time, where the time would be correlated with going from here onward to the right. So the period of this wave would be the time that would be contained within going from its normal state here all the way back to its normal state here, having gone through one full cycle, starting back over. And then we would have, hey, there's another cycle. There's another amount of time or another period of the wave itself. And if this is a cyclic pattern here, just repeating itself, the time it takes to produce one full cycle is going to be the same for every cycle. Because again, we're talking about something that's repeating itself. The behavior is cyclic. So the period of a wave is just, again, the time it takes to produce one full cycle, or the time extent of one full cycle. So that's going to be a really important aspect as well. Then we've got frequency. Frequency is just the number of cycles that occur per unit time. How many cycles occur, say, per second or per minute? Generally, we're going to talk about frequency in terms of cycles per second. We'll get to that, but it's directly related with the period. The period's how long it takes to produce one cycle, and the frequency is how many cycles are produced per unit time. So these two quantities here, period and frequency, are actually inverses of one another. And we'll get to that as well, but that's just something that the temporal aspects, we've got time aspects within period and frequency. And then we've got ourselves wavelength. Oops. We've got ourselves a wavelength here. The wavelength of a wave is the spatial extent of one full cycle. What distance in space is occupied by one full cycle of a wave? And that's it. That's it. We measure it out and say we take a snapshot of a wave. So instead of saying that this horizontal axis is with respect to time, we could say this is just a snapshot of some cyclic pattern at some specific moment in time. And then we could look at, hey, what's the distance that one full cycle takes up? And that distance would be called the wavelength. So it's another way of characterizing waves, but it's more of a spatial aspect of it. So wavelength, well, that's just it. It's the length of one full cycle of the wave. And then we've got the wave speed. And the wave speed is just how fast does the wave travel through whatever material it's traveling through. And it says space here. By space, I don't mean like outer space, just through the surroundings that occupy that particular wave itself. All right, so we've got these 5 fundamental parameters here that we're going to use to characterize waves and discuss them. And that's good to start with. So principal wave parameters and their units. So now we want to be able to unitize things so we know what we're talking about in terms of these different quantities. So if I say something like, hey, the period's 10, first question that should come to your head is 10 what? What are you talking about? I know the period's some amount of time, but it could be 10 hours or 10 seconds or 10 minutes or 10 milliseconds. We got to be wary, and well, you got to be precise about unitizations. Sorry, about unitizations. We need to be able to tell people what we're talking about. So we need units on things. So let's go ahead and go through these units here and talk about how we're going to characterize those. The amplitude. The amplitude is going to really be measured in whatever units are being graphed. So the amplitude is kind of a special case because it depends on what we're looking at. Are we looking at maximum position variation, in which case we have that the amplitude would be measured in units of distance? Or we're looking at the maximum variation in intensity, in which it would be in watts per meter squared. It really just depends on what we're looking at pertaining to a particular wave itself. And that's the one, well, we can have some various units for amplitude. The rest of them are pretty straightforward. Period, we measure in units of time. And what we generally want to measure periods in, time-wise, is seconds. So everybody's on the same page. We'll measure periods in seconds. And I say, hey, the period of this wave is 0.00137 seconds. There we go. We've got some units of time and some numeric value that tells us how much. Frequency. Frequencies measured as cycles per second. How many cycles occur per unit time? Well, again, if we're using time as seconds, we have frequency would be cycles per second. And what we call cycles per second are hertz. So hertz is what we utilize to unitize something measured in cycles per second. So hertz just means cycle per second. But it's easier to just say hertz instead of cycles per second. And it's actually named after Heinrich Hertz, who was a physicist, mathematician that did a bunch of studies with frequencies and all sorts of things, mostly with electromagnetics, but he has the honor of having the name for the unitization of cycles per second. Nice. So get used to hertz and just note that that's how we're going to characterize frequencies. So I can say, hey, we've got this sound that has a frequency of 262 hertz. And that would mean that that sound has 262 cycles occurring per second. Oof, that's a lot, but that's what we've got going on. Then we've got ourselves a wavelength. Well, we're measuring a distance, right? So it has to have units of distance. And for us in this class, we're going to use feet just because it's more familiar for most people. And typically in a physics class, we'd use meters, use SI units, but not going to use meters. We're going to use feet, again, because of the familiarity, and that's perfectly fine. So when we measure wavelengths, we're going to measure them in feet. All right, spatial extent of one full cycle, the wavelength. So times in seconds, distances are in feet, and then we've got the wave speed. Well, wave speed is a measurement of distance per unit time. How far does something travel in a certain amount of time? Well, again, since we're using distance as feet and time as seconds, we're going to measure our wave speeds in feet per second. So that's great. Well, for waves traveling through air, sound waves, that is, at 20 degrees Celsius, we have that the speed of sound in air is 1,128 feet per second. That's how fast sound travels. So someone's across the field from you and they yell, it takes time for that sound wave correlated with the sound that they're making to go from them to reach your ear. Well, if you're pretty close, you probably don't notice that there is some lag in time between them saying it and you hearing it. But if you get pretty large distances away, you'll find that hey, there's this lag time. A good example of this is like at fireworks shows. You're generally pretty far away from the fireworks. They go up, you see this bright flash of light, and then depending on how far away you are, you hear the boom after you see the lights. And it can be a significant amount of time, maybe a second, maybe 2 seconds, but there's this lag because the speed of sound in air is finite. It takes 1,128 feet per second, or it travels at 1,128 feet per second, which is roughly a fifth of a mile. So something that's a mile away making a sound takes about 5 seconds to reach you. But it's some nice things there. So we're always going to be talking about sound traveling through air. We're going to assume that we're at 20 degrees Celsius, normalized conditions, and we're going to use this as the speed of sound in air for everything. Anytime that we want to measure something in terms of like the wavelength, we're going to use this as the wave speed. All right, so we got those five things, we've got the unitizations, and now we want to start looking at some sound waves themselves. So what, again, we want to look at here is how does the vibration itself produce a wave? Something vibrates. Again, you can take like a tuning fork with its rods or its forked ends vibrating back and forth. Well, that's going to vibrate the air molecules next to it back and forth. And we get this chain reaction. So what we have is that sound waves travel as longitudinal waves. And what we mean by longitudinal is that the molecules that house the waves, the air molecules, they vibrate back and forth in the same direction that the wave's traveling. So let's go ahead and look at some different types of waves so we can get exactly what this is saying. And we're going to go look at Dr. Dan Russell's acoustics page. He is a professor at Penn State, and he does acoustics there. He has some nice animations. Make sure I'm showing this correctly. Not. There we go. All right, so let's go ahead and just look at a couple things here. What's a wave? Well, we already kind of discussed that a little bit, but a wave is really just a disturbance, some variation that travels through some material. It could be sound wave. It could be people doing the wave at the Dodgers game. Could be a water wave. It's just a disturbance, some variation in position or amplitude that, excuse me, some variation in position or intensity or something, some variation that is being transmitted. So this would be known as a transverse wave, something where we have that the motion of the material is perpendicular to the direction that the wave's traveling. So you see here, this little pulse, this is traveling to the right, but the material itself goes up and then back down. It's going up and down perpendicular to the direction that it's traveling. It's a little bit easier to see if these old people go up and down, but the wave itself travels to the right. That is a transverse wave. Sound doesn't travel as a transverse wave. Sound actually travels as a longitudinal wave, where the particle displacements are in the same or aligned with the same direction that the wave itself is traveling. So now we've got something like this, producing a little pulse. So you can again think of this as the bar of, of a tuning fork that's going to vibrate, and we just look at one little vibration that it produces. But these air molecules are right next to it. They get pushed forward, they get pulled back, but they do the same things to their neighbors. And ultimately, we've got this pulse, this variation that travels through the material. This is how sound travels through air, much like this. Now, of course, this is just one little pulse. We can have something that's continuously vibrating back and forth right here. They don't show it, but we could have something vibrating back and forth right here at some nice steady rate that produces this cyclic pattern in the air itself. So we can have these traveling waves here, these waves that travel across this material, and they're continuously being produced here. If we look at any one of these individual particles here, notice that the particles aren't moving across the whole material. Particles are just moving back and forth, some little distance. But the wave itself travels to the right over the whole space. But really, it's just a matter of how the individual particles are vibrating back and forth. They bunch up in some locations, and those bunches travel through the material, and they spread apart in some locations, and those spreading apart locations travel through the material itself. But again, you look at any one of these individual little molecules, and all they're doing is moving back and forth, back and forth, back and forth, back and forth. Well, they're actually moving back and forth in the same exact manner that whatever's making them move back and forth is vibrating. So we come back over here and say there's this tuning fork bar here that's vibrating back and forth. It would be vibrating back and forth in the same exact manner as all of these individual molecules, just not at the same exact time necessarily. The only ones that are doing it at the same exact time are these ones. And then there's these different lags depending on where you are that determines when these air molecules are going to be vibrating back and forth with respect to the source itself. But everything does exactly what the source is doing in the end. So the vibration that the source has is preserved within the vibration of the air molecules. Then you put your ear right over here. And these little air molecules here right next to your ear, they make your ear vibrate. They make your eardrum vibrate in the same exact manner that the source over here is vibrating, because all these little air molecules carry that vibration. And then, hey, the little nerve cells in your ear that are sensitive to that particular frequency vibration are activated. Boom, your brain perceives that sound. And that's it. So this is, again, how we have these waves traveling. We have some source over here producing the vibration. We have this material through which that vibration is carried. And then you put your ear over here and you have the receptor, something to perceive the source itself or the vibration itself. So just some other ways of noting things. We have that these individual air molecules are vibrating back and forth. That's true. So we could start to really look at the pattern that they vibrate back and forth at. And this pattern right here, if I just track this little air molecule right here and I plotted out what it's doing, it's moving to the right, and then it's moving to the left, and then moving to the right, and then moving to the left. And it's just doing the same thing over and over. Well, if you remember that sine wave that we looked at, that sine wave could be really looking at this particular particle's motion throughout time, where I could say that it moves back and forth by one what? 1 millimeter, say. I don't know. Or that could be 10 millimeters, but it moves back and forth by some distance relative to where that particle would be if there was no sound traveling through air, which would be right in between the ends. So right about where I have the green arrow pointing would be its normal position. And we could say that that's 0, then it goes to the right by 1 millimeter, back to 0, to the left by 1 millimeter, back to 0, to the right, to the left, to the right, to the left. And I trace out that sine wave with respect to time. Or we could look at the compression and rarefication zones of the wave itself. So where we have all the particles bunch up together, these locations, yeah, they're traveling to the right. That's good. And we've also got in between two bunches, we have this zone where there's not as many particles, and we call that a rarefication zone. So the compression zones are where all the particles are sort of pressed together, and then the rarefication zones are where they're mostly spread apart, or spread apart more to a greater extent, we'll just say. So if I went ahead and tracked these compression and rarefication zones in space, took a snapshot of this, I would have some are tightly packed, then it goes into lowly packed, tightly packed, lowly packed, tightly packed, lowly packed. And there's this variation where I have a high intensity or a high amount packed together, then it varies down to a low amount, then it goes back up to a high amount. And I could again plot out that same sort of sine wave. It would just be characterizing something else. It'd be characterizing, in this case, like pressure variation with respect to time. But in any case, as long as we have this cyclic behavior here, we have a sine wave that we can identify with the sound itself. Whether it's the vibration of the molecule back and forth, or it's the changes in pressure that correlate with the compression and rarefication zones that are occurring over time. And that's what we want to be able to do. So let's look at a couple other things here. Go back, space and time. So this would be like a wave function here. Not going to worry about the mathematical aspects of this, but what we do want to just note is there's a couple of different ways that we could look at things. We have this dynamic wave right here. We have that it's traveling across this area. And if we look at this little particle right here, particle goes up and down, that traces out ultimately the position of the wave along this particular position with respect to time. And if we plotted out the position of the wave at this particular point in space, right where this red dot is with respect to time, this is the plot that we get. We end up getting a sine wave. Well, that's what this looks like. Then you've got this right here. This is just a snapshot of the wave itself at a particular moment in time. Right now, there we go. We take a snapshot of it. That would be the wave laid out in space. So there's different ways that we could, again, discuss things and different informations that we could extract from different ways of discussing things. If I'm looking at the change in position with respect to time, hey, I've got, well, amplitude versus time. I've got some temporal characteristics where if I can look at this and say, hey, these are the changes in position or change in pressure with respect to time that is occurring, I can extract out something like the period, right? Here's the changes in pressure that are occurring. I have one full cycle. I can come down here and read off how much time is contained in one full cycle. And it looks like about 5 milliseconds or so. Starting at 10. This one's the 20. Not quite 5. That's hard to kind of say. I'll bring that down. What is that? Maybe more like 8 or something, 7.5 milliseconds, but I could get out the period from this one. Or from this one, I have the wave laid out in space. I've got the amplitude of it. And what we have here, the position. We could have that this is in feet, and then I can measure out one full cycle of the wave and get how many feet it is. So once we have this, I could start here, come back over to here and say, hey, what amount of distance is that? It looks like it's about 10. 10 what? Well, we put units on it and say 10 feet. And there we go. This one gives us the ability to extract out the period. This one gives us the ability to extract out the wavelength. Those are just, again, different ways of looking at the same wave. Variation of a point through time, or the variation in space at a specific moment in time. Fantastic. All right, let's go back. All right, so now what we want to be able to do is distinguish between different types of sound waves that produce tones and, well, some that produce non-tones or atonal sounds. First off, when we talk about tones, we talk about certain types of sound that have a special characteristic. And that special characteristic is that they're periodic. If it's a tone, if the sound that is under discussion constitutes a tone, it has to be periodic in the vibratory cycles itself. That is, that it has to have a repeating element, that the vibration itself has to do the same thing over and over and over. Well, when we talk about a pure tone is just one singular vibration, one singular frequency, and that's identified as one singular sine wave. So if we went back to something like this and said, hey, this is a graph of a particular sound. This would be that of a pure tone then. because we'd have one sine wave. It's doing the same thing over and over, and that's it. It's a cyclic pattern. It's a single sine wave. This would be a pure tone. Well, there's also what are known as complex tones, and complex tones are just combinations of pure tones, but they are combinations such that the overall pattern is still periodic. It still does the same thing over and over. It just looks a lot more complex, because what you end up having with a complex tone is you have multiple frequencies, multiple pure tones in a sense, superimposed on one another. That if you have multiple pure tones, it's no longer a pure tone, it's now a complex tone. And what we'll have is there's certain criteria to produce a complex tone, but the end result is that it is periodic. It has a well-defined cycle. It has something you can identify as a pattern that repeats itself. Most tones are actually complex. Pure tones we can generate. There's some things that'll produce pure tones naturally, but most tones that we hear are that of the complex nature. So let me just show something really quick here. This here, this is a picture of a sound wave. Now, you may say, well, I don't see anything moving back and forth. Well, this is a plot. This is a plot of the pressure variations that are occurring with respect to time when a trumpet's being played. Trumpet playing a single note, playing one sustained note. This is what the pressure variations look like with respect to time, which correlate back individually with the individual molecules through air bouncing back and forth. But it's complex, right? It's just not that it goes to the right, then goes to the left, then goes to the right, and goes to the left. It goes to the right, then goes down, then goes to the right again, then down a little bit, and back and forth. It jiggles around in some complex way. The pressure is changing in some complex way. And what we have here is a complex tone. The way that I know it's a tone is because it's repeating. It's doing the same thing over and over. There's this repetitious pattern here that I can see. And if you can see the pattern, then if we're talking about sound waves, that would constitute a tone. And this would have tonal aspects to it, where we can have a well-defined cyclic pattern, a well-defined note in a sense, and discuss other properties of it. Not all sounds are tones. Sounds can be atonal, have no tone associated with them directly, where they don't really have a musical note in a sense that you could correlate with it. You knock on a door. A knock on the door could have a low or high sort of frequency associated with it, but it's not a tone. If we looked at someone knocking on the door, a sound wave from that, you're not going to get a repetitious pattern here. You're going to get something that is more distorted, something that is more chaotic in a sense. There is no repetitious cycle. And when you have something like that, you still have a sound, you just have a sound that's not tonal. Tones are really important. They're really nice because they're easy to analyze. And that's what we're going to mostly stick with in this course, is analyzing tones themselves. So going back to this right here, pure tone, just a singular sine wave, singular frequency oscillation here. Complex tone, we have multiple frequencies occurring simultaneously that superimpose themselves on one another and produce some complex pattern. That complex pattern is still periodic, though. Again, if it's a complex tone. And that's what we've got. Then we've got the quality of the tone itself, which we generally refer to as timbre. Timbre of a sound really depends on the frequencies and the amplitudes of each frequency of which the sound is composed. So now you start having, well, you've got a complex tone that has multiple frequencies. And depending on the contributions of those individual frequencies, the sound will have different identifying characteristics, its own uniqueness in a sense. What distinguishes the piano from the guitar, for instance? You play this note on the piano, you play the same note on a guitar, they sound different, even though it's the same note. What it ultimately comes down to there is that the the frequencies in both of the sounds, if it's the same note, will all be the same. But the amplitude of the individual frequencies will not be the same between the guitar and the piano. And that will produce this difference in timbre, which is an identifying quality of the sound. And that's something we get to way down, but just kind of talking about it a little bit right now. The idea of timbre, quality of a tone, its identity in a sense. All right. So, main thing, pure tones, single sine waves, complex tones, multiple sine waves superimposed to produce a complex pattern, but that complex pattern remains periodic. That's the important aspect of complex tones. So let's think about making a complex tone, synthesizing something here. Synthesis, hey, just a process by which we take more than one element, combine them together, and produce something new. For sound waves, hey, we can take a pure tone and then add some more frequencies to it and produce something new. If we add them, these new frequencies to this pure tone in a certain way, we can get a complex tone itself. So let's look at these. Zooming in a little bit here. So look at this. We got two separate sine waves right here. We got a red one and a blue one. How many full cycles of that red sine wave do you see? You can come count it out, right? We're going to start right here. We go up, we go down, we go back up, and we're back to where we started right there. There's one full cycle going from here to here. And then what? We go up and down again, over here, then up and down again, and then we're here. We've got three full cycles of this red wave, right? All right. And then we've also got this blue wave here. Well, what about this blue wave? How many cycles of this blue wave do you see? Well, we can start counting them out as well. We got one full cycle, two full cycles, three full cycles, four full cycles, five full cycles. So note we've got five full cycles of the blue wave, but exactly within one full cycle of this red wave. And then what's going to be going from here to here? There's another five full cycles of that blue wave. And then from here to here, there's another five full cycles of that blue wave. So in this picture here, we have three full cycles of the red wave and 15 full cycles of the blue wave. And we want to add these two together. So when we add them together, it's just we superimpose them on one another. We have these peaks would add together. And then we have places that would subtract, where we have this part here and this part here are in opposite sides of the zero mark. They would end up subtracting off of one another. Ultimately, what you do is you just go piece by piece, part by part, and add up the individual displacements or individual positions of the wave at some moment in time and see what you get. So we add these two waves together, and this is what ends up resulting here, is that, hey, we get a new pattern that is cyclic itself. If we count how many full cycles of this pattern we have here, how many full cycles do you see? And again, we go up, we go back down, dance around a little bit, and then we're back to where we started. And then it does the same thing again, back to where we started, does the same thing again, back to where we started. So there is 1, 2, 3 full cycles of this new wave that's produced from these two waves here. let's look at some other things going on here. Well, this red wave has one full cycle that occurs in some amount of time. Well, we could look at the amounts of time right here because we're told this is time in seconds right here. We start at 0, we go to 1 second, and that's one full cycle has elapsed. One full cycle, then another full cycle in another second, and then another full cycle in another second. Hey, this is 3 seconds of this wave shown here, and we've got 3 cycles of that red wave. All right. So let's go again and come back over to this picture and see what we've got. How long does it take to produce a cycle for this new wave here? Well, if we look at the cycle, hey, it's complex, but one full cycle occurs in 1 second. The next full cycle occurs in another second, and the next full cycle occurs in another second. Hey, there's 3 full cycles that occur in 3 seconds for this complex wave. That's the same as for this red wave. This red wave is ultimately dictating how the new wave is going to come out because we are adding in a particular other frequency that is directly related to this red wave itself. So let's see a couple things here. Could we say first what the period of the red wave is? And yeah, we can, because we just looked at it, right? The time for one full cycle, hey, that's 1 second. So we've got the period of the red wave, 1 second. What's the period of the blue wave then? Well, the period of the blue wave is going to be 1/5 of a second, right? The time it takes to produce one full cycle for the blue wave is much, much less, 5 times less than that of the red wave, because 5 cycles occur in 1 second. One cycle has to occur in 1/5 of a second. So let's think about now, not the period, but the frequencies of these 2 different waves here. This red wave has a frequency, number of cycles per second, right? That is what the frequency is. We have 3 cycles in 3 seconds. So 3 cycles divided by 3 seconds gives us 1 cycle per second. Well, yeah, that's right. There's 1 cycle that occurs every second. There's the frequency. We'd say the frequency of this wave is 1 hertz. What about the blue wave? Well, the blue wave, we have 5 cycles occur every second. We could take the whole thing and say, hey, we've got 15 cycles in 3 seconds. 15 divided by 3 is 5, which gives us 5 cycles per second. Or we could just note that, hey, there's 5 cycles that occur within 1 second. There it is, 5 cycles per second. Either way. So if I wanted to say what the frequency of the blue wave is, go ahead and say, hey, that's 5 hertz. So we've got a 1 hertz sine wave and a 5 hertz sine wave that are added together. And they add together to produce this new complex wave. And we could ask, what's the frequency of this complex wave? Well, you go back to the frequency of this complex wave. There's 1 cycle that's occurring every second. 1 cycle per second is 1 hertz. It's the same as the frequency of the red wave. And this is because the blue wave that we added in has a frequency that is an integer multiple of the red wave's frequency. And that's something that we're going to expand on as we go on, but that's an important aspect in producing periodic complex tones. For a tone to remain periodic, when you add in new frequencies, those higher frequencies that you add in must be integer multiples of what we call the fundamental frequency, or the lowest frequency in the sound. And that's how we get complex tones. But more so right now, again, just want to get the idea of individual sine waves being added together to produce new periodic patterns that constitute complex tones. We take away the blue wave, we just got a 1 hertz sine wave that would be correlated with a pure tone. We put the blue wave in there, boom, we now got a 1 hertz complex tone. It's still 1 hertz. It just different, different. They're going to have different sound qualities to them. And that's, again, stuff that we'll expand on. All right. So moving on here, we've got analysis. What is analysis? Analysis is just breaking something up that's complex into its individual components so you can examine them. So I could take something that's complex, like a complex wave, and I could break it into the individual sine waves that it's composed, the individual, I don't want to call them pure tones, but the individual frequencies of which it's composed. And then I could analyze what the individual contributions of those individual frequencies are and get an idea of why the sound sounds the way it does, why it has these certain qualities, these certain characteristics that I can hear. And that's ultimately what we're going to build up to in this course, is be able to take a complex tone, resolve it into its individual frequencies, and understand why it sounds the way it does in both its pitch and just its quality itself. And that's going to take some time, but we'll get there. That's going to be hoped along by some programs. So waves in time and space, we looked at this on Dr. Dan Russell's page. Just say it again here. We can look at a wave in time where we look at a specific point in space. And as the wave passes through that point, we track what's going on there, whether it's the pressure variations at that point or whether it's the displacement of the air molecules at that point. Those two things are correlated with one another. We've got some wave in time, where when we talk about waves in time, we have the characteristic parameters being the period of the wave and the frequency of the wave. Those are two time correlations there. If I take a snapshot of a wave, I have a wave laid out in space, and then the characteristic parameter that I can extract is then the wavelength. And from either of those, we can get more information. The pitch of a tone. So when we start to talk about pitches of tones, we can start thinking about musical scales and stuff like that. But right now, don't really want to go there. Ultimately, just want to have an idea of high pitch versus low pitch. You have something high pitched, or you have something low pitched, low. And those are relative, right? Relative to one another. Something high pitch, something low pitch is just really coming down to its frequency. So the pitch of a tone itself is a characteristic of the sound related to its fundamental frequency. If you recall what we're just talking about regarding the fundamental frequency is that it's the lowest frequency in a periodic sound itself, periodic sound wave. So again, we got to be talking about a tone here. Only a tone has a fundamental frequency. Atonal sounds do not have fundamental frequencies, but tonal sounds do, and that fundamental frequency actually defines the pitch of the sound. If we looked at musical scales, which we'll do in a little bit, not at everything, but if we looked at the notes, the musical notes and how we define them, they are defined by specific frequencies. And the frequencies that they're defined by are the frequencies of the fundamental frequency. That's how we discuss tones themselves in terms of their fundamental frequency. And that fundamental frequency goes into the pitch. The higher the fundamental frequency is, the higher the pitch is. The lower the fundamental frequency is, the lower the pitch is. So you think about a piano and you've got the keys to your left, which are the really low pitch keys, and then the keys to your right, which are the higher pitch keys. And it's all just relative, right? But each of those keys itself has a specific fundamental frequency that it rings at or resonates at. Middle C. So again, we get to something with the piano here. Middle C, the lower vocal range of a soprano, all right. But really, it's a note with a frequency, fundamental frequency here, of approximately 262 hertz. 262 hertz, 262 cycles per second. That is the middle C, which is also known as the note C4, which is the fourth octave of C, which is at the middle of the modern piano. So C4, that's middle C, 262 hertz is what frequency defines that particular musical note. And we'll be looking at that here shortly. Timbre, again, just a characteristic that correlates with the quality of a musical note, or quality of a tone, should really just say. Doesn't necessarily have to be a musical note. The characteristics that define the perceived quality of a tone. And it's really the identity of the sound itself. What are the frequencies and what are the individual amplitudes of those individual frequencies that all come together to give that sound its particular uniqueness, or that tone its particular uniqueness. Sometimes timbre is referred to as sound quality or color, brightness, darkness. There's different ways of discussing, talking about timbre, like, oh, that tone's so bright and colorful, or it's so dark and drab. But those are really, again, going to be correlated with what frequency bands are accentuated, what frequency bands are more muted out. And again, this is going to be stuff that we look at as time goes on. So the reading, chapter 1, chapter 2, I'm going to go through these, some of the key concepts here, 1 through 4, 9 through 20, 19 through 20, 28 through 36, 41 through 47. Some of this is historical, but some of it reinforces things that we have just discussed now. So do some reading. And then we've got the assignments for this week. So we've got some Audacity. Download it. You need it. Reading, quiz for section 2, lecture for section 2, a lecture outline, for section 2. And then we've got an experiment that requires Audacity. So what we're going to do is we're going to take a look at that, and then that'll be that. So come over here. And we're going to go on down to section number 2. Right here, we've got ourselves section 2 experiment guide, pure tones. This is generally how the experiments are going to work. There's some guide that you work through. You work through the guide will ask generally for you to note something and or to take screenshots. Screenshots, again, if you're not sure how to take screenshots with your computer, producing screenshots and PDF files right here. Please don't use pictures from your phone. Take screenshots. Pictures from your phone do not come out clean. Screenshots come out very, very clean. All right. So it'll ask you to take some screenshots, write descriptions for screenshots and full sentences, and then you're going to upload that right here. So let's just take a look at the experiment guide, and then we can discuss some things further. All right. So experiment guide, pure tones. So you're going to read through this stuff here, but ultimately we're going to produce a musical scale. And I'm going to show you how we're going to do this here. But notice some things right here. Follow the instructions, answer the questions, take screenshots of your program use where asked for, produce a singular PDF file of your screenshots and table. Each screenshot should include a brief description of what is being shown located directly below the given screenshot. Though brief, full sentences should be used. So you're going to take multiple screenshots throughout this experiment. In the end, each individual screenshot should have its own description of what it is actually showing. That description should have full sentences utilized, not just shows a wave. It should describe what's being shown and use full sentences, please. Those should all be combined into one singular PDF file and uploaded. It says experiment 1. I changed things. This should say section 2 experiment. But you upload it Section 2 experiment upload link in Canvas. So I'm going to show you this specifically, but kind of goes through, hey, open up Audacity, produce a mono track, blank track. You're going to add some stuff in, 262 hertz. This isn't all written out, but it goes through, shows you things. All right, step by step, step by step. But in the end, you're going to continue. You're going to produce 8 tones here linked all together. And then right here, it says, take a screenshot of the screen and save it for your upload. So here's where you take a screenshot of what your screen is showing you for Audacity. And it should look very, very similar to this. Very similar. And then it starts to have you zooming into specific locations. There's zoom tools, all sorts of stuff. So you can see the individual sine waves that we've constructed or synthesized in this. And then it tells you to go on and highlight certain sections and make some measurements. And great, take screenshots of this entire screen, save it. So you're going to have something like this. You're going to take a screenshot of it. Boom. It should look fairly close to this. Maybe not exactly the same. You might have something highlighted from peak to peak, but it should look similar to this. And you're going to save that. Write down the number of samples displayed. Once it's circled in red here, well, you're not going to have to circle it in red. You're going to write it down because there's a table that you have to fill out as well. So produce a table, fill it out, blah, blah, blah. Take a screenshot of your entire screen showing the cycles highlighted and the number of cycles. So this is, again, like the screen that you're going to be taking screenshots of. And again, it tells you to continue to do this at different points in time and continue to take screenshots. Ultimately, you're going to have 9 different screenshots and 1 table filled out. Each individual screenshot should have a brief description directly below it explaining what is being shown, always useful sentences for descriptions. Produce 1 singular PDF file, and that will be what you upload. Kabam, done. Now, this looks like a lot, but once you get it down, it goes pretty quick. So what we're going to do right now is go ahead and take a look at how you do this. So I'm going to open up my Audacity here. Share sound. Audacity, great. So this is what my Audacity looks like when I open it up. If you've got Mac, it's going to probably look a little bit different. And it may be something that looks like, come back down, sorry. Let's jump around. Controls for Audacity for different system views. It may have things that look a little bit different in certain locations. So you can check this out, but in the end, you should have something that is at least somewhat familiar, has some tools, different things going on. But if something's not looking right, like, oh, I can't find that, look in here. It may be in there. I have Mac, but I can't write instructions for every operating system. It just doesn't really work out. At any rate, this is what we've got. Here's Audacity. That up there. So the first thing that we're going to do is we're going to add a track. So go up here to tracks, add new. We want a mono track. Kabam, stick in a mono track. Fantastic. Then what we're going to do is we're going to generate a tone. So once we've got a track there, I can go generate and go to tone, click on that, and then this window comes up and it says, what kind of wave do you want? Well, we want a sine wave. It should be defaulted to sine wave, but make sure. And then in the experiment guide, it says start off with a 262 hertz wave, and the amplitude, I'm just gonna leave it at 1. And then the time. So I want to change this 4 to 1. And these, there's a little decimal place right there. Oops, little decimal place. So this would be 1.2 seconds. I just want it to be 1 second exactly. So that's going to be the length of this 262 hertz sine wave. Press OK, kabam. There we go. We've got ourselves 1 second. Got a sine wave here. Fantastic. Well, let's see something just to be able to see stuff. I could zoom into this. So there's these different tools that are located somewhere. This little spyglass is here, or you may see up in the view here, you could go zoom, zoom in, zoom out, control 1. There's different ways of zooming. The easiest way, in my opinion, is hey, use a little zoom tool. And I come over here in the wave, and you can right click or left click. Right click, zooms in, left click, zooms out. That's again PC control. You can zoom in and see, oh yeah, this is just nice sine wave. That's it. This does the same thing over and over. And if I asked you something like, how many full cycles do you think are shown right here? Well, we've got 1 full second, right? And we've got that this is a 262 hertz sine wave, 262 cycles per second. We've got 1 second, then there's 262 cycles. Excuse me, 1 second, 262 cycles there then. All right, that's a lot of cycles. Let's listen to this. Let's hear what this sounds like. Speakers, again, I don't know how loud stuff comes out on your end, but count it down. 3, 2, 1. Oh, hear that? That's the note C4. We're really, really close to it. 262 hertz. That's what 262 hertz pure tone sounds like. Sine wave. Great. All right. So we've got something going for us. I'm going to go ahead and zoom out some so I can make some more room. Eventually, we're going to have 8 of these blocks in here, but each one's going to have a different frequency. So what I'm going to do now is I'm going to go back to the selection tool. The selection tool lets me click in here and select specific parts, or I could highlight specific parts, all sorts of things. But what I really want to do is I just want to select right next or right at the very edge of this first part here, because I want to generate another tone here. So I'm going to go ahead and go generate a tone, and 294 hertz, I believe, is the next one. Sine wave, boom. Another 1 second interval, but now it has a different frequency. Let's go ahead and play this. Play it from the beginning there. Ready? They sound different, right? We've got 260 hertz and 294 hertz. We've got C4 and then something that's not C4. Wow. Wow. All right. So one thing to note there is that the frequency is getting higher. The sound has a higher pitch. That's it. It's correlated directly with the frequency. We're gonna do another one. Select right here, and then generate another track, another tone, excuse me. This one, you do 330. Stick that one in. Let's play all 3. Do, re, mi. Look at that. Starting to produce some musical scale here, right? So what you're going to do is you're going to continue to do the same thing there. In the guide, it tells you the frequencies of each. There's a next one until you have 8 of them. And then skip to it here. Have something like this. Oops. Can zoom to fill the screen here. And let's play this. Oops. Select where to start. Wow, look at that. This is what you're going to produce. C major scale, bam, do, re, mi, fa, sol, la, ti, do. And that's a screenshot right there. Kaboom, there's your first screenshot. Well, what are you going to do next? Well, the next part is where we really start looking in on this wave, and we're going to make some measurements. So in order to do that, we're going to have to zoom into specific locations. Now, there's a way that the guide says to do it, and there's some alternative ways that you may do it as well. But ultimately, you are going to zoom into each individual sound, 8 of them, and you're going to measure out one full cycle. So the way I have it in the guide is to select a little portion right there, and then select a little portion like this. So I use the zoom tool, and then I just got a little bit to the left and a little bit to the right of 1 second. So I have actually 2 different portions of the sound right here. I let go, and here is the separation between, well, the 262 hertz and the 294 hertz. Now I'm going to zoom in a little bit more, keeping this center here, and zoom in so I can see a few cycles on either side. And then this is what you're going to do. You're going to go to the selection tool, and ultimately you are going to highlight one full cycle of the wave. So this is the 262 hertz wave. Be as careful as possible. Careful as possible. That's not one full cycle. That's more than one full cycle. This is not one full cycle. That's less than one full cycle. This is good. Maybe it's not exact, but it's going to have to be close enough. There's limitations to our accuracy here. Or I could start here and go, hey, this right there is about one full cycle. But it's somewhat a little bit easier to start at the zeros. Just make sure you have one full repetition of the wave. Start there where it goes down, then up, then back down, then starts over. Start here where it goes up, then down, then back to where it started. Either way, you have the ability to highlight one full cycle. Now, there's a setting that we have to change, a couple of them actually. And this is where you have to be really careful. A lot of mistakes happen here, but it is imperative that you make sure that you change this right here, this to length. And well, as long as the length's in there, you're good, but I just pick length and center of selection. If you're on Mac or even on some PCs, that shows up in a different location. And I want to show that really quick because this is a big thing that people have some issues with sometimes. So I know a lot of people using Mac, that's fine. But that control to change to length and center of selection is in a different spot. And it's like over here, there's this little gear here that opens up a menu, and that's where you have length and center of selection. And then you have these 2 readouts here, length and center of selection, not this. So let me go back to my view here. I have length and center of selection here. Once I have that, this one here, this readout right here, that's going to be the length. And this one here is going to be the center of selection. This here, I don't want to use. This is nothing that I'm interested in. We are interested in this really, the length. So number one, make sure that you change to length and center of selection. And then number two, you have to change what these read for this particular experiment. The default setting is hours, minutes, seconds, and milliseconds, something like this. We don't want this. You want this to say samples, and you have to go in and make sure you select samples. So it should say samples right here. So now we've got this. We've got that the amount that I have highlighted correlates with a certain number of samples. That's the length right here. The length that I have highlighted has a certain number of samples in it. You say, well, what do you mean samples? Samples are just little bits of information. There's 169 bits of information in this little region that I've highlighted here. And then there's a sampling rate for the system itself. The system is set to sample at a rate of 44,100 samples per second. That's the sampling rate, and that just has to do with how fast it reads the information. At what rate does it read the samples? And the samples contain the information about the sound. So what's important with this? Well, the important aspect is going to be this, is that we can identify one full cycle. And I'm going to click off here. Notice if I click off and I just have this, samples goes to 0. Center of selection, well, that's just how far into into the wave I am in terms of samples. This location here is 43,870 samples into the file. So what? That doesn't really matter. It's this that we want, this length. Depending on how much I have highlighted, notice that the number of samples, the length changes. The more I have highlighted, the more samples I have. So what do we want to do? Again, we want one full cycle highlighted, because one full cycle is highlighted now. I have the number of samples in one full cycle. All right. Well, I've also got the sampling rate. There's 44,100 samples in a second. So what we can do with this is ultimately determine what is the frequency. We can measure the frequency of this in a sense, or calculate it out. And that's going to be 44,100 samples per second divided by the number of samples in one full cycle, 168. So if I do 44,100 divided by 168, check this out. Got my calculator right here. 44,100 divided by 168 gives me 262.5. It says that the frequency of this wave that I've just highlighted out one full cycle of is 262.5 hertz. Well, what did I input it to be? I input it to be 262 hertz. I measured back out, I get something really close to that. And this, again, is really an exercise of, number one, being able to identify a full cycle, and number two, to be able to extract information out of the measurement that we make. And it's going to be something that we do a lot of. So this is just kind of getting used to measuring things, using some numeric values, and doing a little tiny bit of math, division, right? 44,000 divided by the number of samples in one full cycle. That will give you the frequency. So right here, this would be a screenshot. I've got one full cycle highlighted. I've got the number of samples shown here. And there we go. This was the first part of the wave. I can come over here and do it for the second part of the wave. Whoop, there's one full cycle highlighted for the second portion. Notice there's less samples. Oh my gosh, this one has less in one full cycle. 149 hertz, excuse me, 149 samples. Well, you do 44,100 divided by 149, and you're going to get something really close to 294. Well, that should be truth, because that's the frequency that we made the second portion of the sound be. So this would again be another screenshot. Description, We've got one full cycle highlighted of the second portion of the sound, showing that there are 149 samples contained in that one full cycle. There's a description. Kabam. So what you're going to do is you're going to do this for each individual section. So I can come back out. Now I've done the first and the second. I can come over here, highlight around 3 seconds so that I can get the third and the fourth. And then I can do it again, highlight around 5 seconds so I could get the fifth and the sixth, and highlight around 7 seconds to get the seventh and the eighth. Or if you want to, which is fine, you can just go into the individual portions, just make sure that you're looking at the right one. So I can just come in here, zoom in, highlight one full cycle. Great. Zoom back out, come into the second one, highlight one full cycle. Zoom in enough so you can get a good measurement. So you only have like 4 or 5 full cycles shown. So you get good, nice, clean measurements in terms of identifying the full cycle. And that's it. Go through each individual portion. You'll have 8 screenshots from that, plus the first screenshot showing all 8 together. There's your 9 screenshots. And then that table that you fill out is a matter of those measured number of cycles in a, measured number of samples in a cycle. And ultimately the measured frequency. So you go all the way down, there's this table. Dun, 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 dun. Here it is. Here's the input frequencies, the first, second, third, fourth, fifth, sixth, seventh, and eighth portions of the sound with the number of samples in one cycle. This one should be about 168. This one should be about 149, and they should get smaller and smaller and smaller. And then the measured frequency is the 44,100 divided by the number of samples in one cycle. And these measured frequencies should be really close to these input frequencies. I'd say within 10% of them. So maybe you're off by 3 hertz here or 5 hertz here. That's not that big of a deal. If you're off by more than a couple hertz, though, you're probably either not calculating it right or you're not highlighting a full cycle correctly. And those are things that happen. Make sure that you change it into samples. Make sure that you're looking at the length of the portion and not something else, which again is something really easy to do. Start looking at this, or a lot of times people look at this one here, and this is not the length. Make sure you're looking at the one that is the length when you highlight. Other than that, run through it. Once you get it down, it goes quick. Boom, 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 boom. And that's pretty much that. Questions? Alrighty then. Well, that's it. Yeah, that's not much else to say. Question. Thank you. Oh, thank you as well. All right, then I'll leave you guys be. Have a great rest of the day, great rest of the week, a nice weekend, all that good stuff. And see you back next Tuesday. I'll send out an email reminder. Probably try to do 10 o'clock, but I might have to shift it a little bit time to time. But anyways, that's it. Get this experiment in, and we continue on. Have a good weekend too. Take care.
Thank you.
Thank you.